Hello everyone and welcome back. We're going to continue with the Oscillations chapter. It's not a very long chapter, so we're almost kind of done with it, about 1 hour, and we'll be finished with it. So let's continue with it. Last time we stopped on vertical springs or vertical oscillations, so let's do an example on those. We have an 83 kilogram student hangs from a bungee cord with a spring constant K equal to 270 newtons per meter. So if you don't know what a bungee cord is, don't worry about it. Just imagine it's some kind of a spring, and it can stretch, and it's stretchable, and it has a force constant of K equal to 270 newtons per meter. The student is pulled down to a point where the cord is 5 meters longer than its unstretched length, then released. The student is released. So this, as you could imagine, the student will just vibrate or oscillate up and down. Where is the student and what is his velocity 2 seconds later? In order to answer this, let's draw something, and then we will answer the question. So come here. So here is imagine this is the cord, and I will draw it like a spring. Looks like this, all right? This is nothing attached to it. It has some natural length. Now, if the student is attached to it, but you very carefully lower the student until the student just sits there, does not oscillate up and down, then here's the situation. It would look like this. We drew it last time. It looked like, here is the student here. This is the student of mass M. So this is delta Y. This is delta Y. Now the student, if you just lower him or her carefully, and just let them here, then they will just sit there. Do not move up, do not move down, they're just hanging in there. If you lower them even further and then let go, then they will start to oscillate. And they oscillate about this equilibrium position as we have shown last time. I might show it one more time. So let me see here. So what we did, or what they did, was lower the student a distance 5 meters below the natural length of the spring. 83 kilogram hangs from a bungee cord with a force constant of 270 newtons per meter. The student is pulled down to a point where the cord is 5 meters longer than its unstretched length. So this is unstretched cord, and the student is here. So this is 5 meters. So let me just show you there. So I know this is 5 meters. In order to calculate the amplitude, you see the oscillations will be about this point. The student will go up and down about this point. This will be the new natural length of the spring. And I want to know what delta Y is, and then I can figure out the amplitude. The amplitude is how far you are from the equilibrium point. This is the equilibrium point. So I want to know what this is. So I need to figure out delta Y. So if you hang something on a spring, when the student is just here, then you got the force of the spring this way, and then the mg downward, and the force of the spring is the spring constant times by how much you stretched it, and the stretch is delta Y. So it is K times delta Y, and so K delta Y is equal to mg, and therefore the delta Y will be mg over K. So let me write it here. Delta Y will equal to mg divided by K. And let's actually calculate that. I do have my calculator with me. So I have 83 kilograms. So the mass is 83. So 83 times 9.8 divided by K, which is 270, I believe. Let me see. Yep, 270. So that's 30.01. That's 30.01 meters. That's delta y. I'm sorry, not 30, 3.01, not 30. So yeah, that sounded like a lot. Yeah, 3.01 meters, essentially 3 meters. So delta y is 3 meters, therefore this distance here, that will be the amplitude. This is, I'm measuring from here. It's actually up to here. I'm measuring to the bottom of the spring, bottom of the spring. Okay. So this is 5 meters. This is about 3 meters. So this is about 2 meters or 1.99 meters. About 1.99 meters is the amplitude, right? That is the amplitude. And for example, when the student is here, we're going to measure the position y. This is our y-axis, right? This is the y-axis. So when the student is here, this is y, but y is negative. So the forces on the student at this point here are the amount by which you stretch the spring, which will be, the magnitude will be y plus delta y, okay? So it will be, you would have two forces at the bottom here. I'm just doing it again. So at the bottom there, you have two forces. You have the mg downward, and then upward you have the force of the spring, which is equal to this k times this distance. And that distance is, so you have k times that distance. And that distance is delta y, and then plus the absolute value of y. But y is positive this way and it's negative this way. When y is negative, the absolute value will be negative y. So you have negative y, right? If y, let's say, is negative 3 meters, so you have to put a minus sign in front of it to be positive 3, and you add to it the delta y. That's the total stretch of the spring, and that's the force of the spring. And we said the net force equals to the mass times acceleration. The net force will be this, k delta y minus ky minus mg equals to the mass times acceleration. So like this, k delta y minus ky minus mg equals to the mass times acceleration, the mass times the acceleration. But k delta y, let me see, k delta y is equal to mg, so k delta y minus mg will be 0. You just cancel, and you get minus ky equals to ma, and so the acceleration would be negative k over m times y, and therefore y of t, this will be simple harmonic motion, and y of t will be a times the cosine of omega t plus this phi here. That's phi. And let's figure out what phi is for our problem and what the amplitude is. I will just, so for example, since we're saying y here would be the amplitude, the initial amplitude, let me write it here. So just to be clear on everything, we have k, we have y of t, would be the amplitude times the cosine of omega t plus phi. At t equal to 0, y is equal to negative the amplitude. Y is negative the amplitude, which is 1.99. So at t equal to 0, we have this. Y at 0 is equal to negative the amplitude. That's on the left side. But on the right side, it has to equal to a times the cosine of, if you plug in 0 for t, that's 0. And so you just have the a times the cosine of phi. And so negative a equals to a times the cosine of phi. So the cosine of phi is equal to negative 1. So phi here would be pi, because cosine of pi is negative 1. So phi would equal to pi. Remember, everything is in radians. And therefore, I have y of t, y as a function of time, will be the amplitude, which is 1.99 times the cosine of omega t. And omega is the square root of k over m, right? It's the square root of k over m. And so let's quickly do that. K is 270, the mass is 83, so let's get omega. I'll do it here. Omega is the square root of k over m. Let's just calculate it quickly. K is 270 minus m, which is 83. And let's take the square root of that to the 0.5. And I have 1.804. 1.804 radians per second. So 1.804 t plus pi, because pi is equal to pi. For the velocity v of t, you will take the derivative of this. Derivative of cosine will give you negative sine, and then the 1.8 comes out because the chain rule. Derivative of the inside is just 1.804. So 1.804 times 1.99 will give me 3.59. 3.59. Oh, don't forget the minus sign, because derivative of cosine is minus sine. So 1.804 t plus pi. Okay, we're ready. We have the full function now, and we're ready to just answer the questions. Where is the student and what is his velocity? Well, where is he? Where means the position. So y at t equal to 2. Plug in 2 here and see what you get. So let's see. I will do the cosine first. Cosine of 1.804 times 2 plus pi. I'm in radian mode, that's good. And then times the 1.99 in front. This is 1.777 meters. We'll talk about what this means in a moment. So let's just write this. And then the velocity v at 2 will be, plug in 2 over there. So let's start with the sine first. The sine of 1.804 times 2 plus pi. Okay. And times negative 3.59. So the velocity will be negative 1.61, negative 1.614 meters per second. That's the velocity at t equal to 2 seconds. All right. So we have this now. What do we mean by y equals to 1.777 and the velocity being negative? What does it mean? We have to look back at the original picture. So looking back at the original picture, here is our origin. This is the origin. And the student is at y equal, so this is the 0. The student is at y equal to 1.77. So the student is somewhere here at 1.77. His velocity is negative 1.6, so the student must be heading down. So does this make sense? So he starts here. To go from here all the way here and back, that's 1 period. To go from here to here, that's half a period, right? A quarter period plus a quarter period, that's half a period. To go back all the way here, that's 3/4 of a period. So apparently 2 seconds is less than 3/4 of a period. Is it? Well, let's see. Let's just check. The period is 2 pi over omega. 2 pi over omega. Let's calculate the period. We get 2 times pi, 3.14159, divided by omega. What was omega? 1.804. So I get 3.48. So the period, 3.48 seconds. So if you wait 3.48 seconds, the student will be back here. But we didn't wait 3.48 seconds, we only waited 2 seconds. So where is he? So let's divide 2 seconds over 3.48 and see what it is. So 2 seconds over 3.48 is 0.574. So that's slightly more than 1 period, slightly more than half a period. 0.57, half would be 0.5. So slightly more than half a period. So it means the student went from here to here, that's half a period, and now the student is heading down. So everything works out. The position of the student should be somewhere here, and it is 1.77, and the student's velocity is heading down as it should be, so everything looks all right. Okay, so it's always good to double check. I mean, you get these functions. Once you get the y, the position, you take the derivative once, you get the velocity, you take the derivative twice, you get the acceleration. This is everything. Once you get this and it's correct, it's great. But it's good to always, just for a sanity check, just check where it should be in regards to the period and so on. Okay, our next topic is the pendulum, or the simple pendulum. So it looks something like this. You take a mass, you hang it on a string, you tilt it a little bit at a small angle, and then you let go. And it oscillates back and forth. And it actually, now we say it's a small angle because for a reason that you will see in a moment. So let's say here, there are a couple ways to do this, but let me just show you something. So first of all, we're going to use an approximation here that the sine of the angle, sine of theta, if theta is in radians, the sine of theta can be written as an infinite sum. It is equal to theta minus theta cubed over 6, over 6, which is, if you like, you can write 6 as 3 factorial, because 3 factorial means 3 times 2 times 1, so 3 factorial, and then plus theta to the 5th divided by 5 factorial, minus theta to the 7th over 7 factorial, and so on, plus you have theta to the 9th and so on. So if theta is small, then imagine theta is 0.1, then theta cubed will be very small. And theta to the 5th will be even tinier, because theta to the 5th. And you get this formula here. And this formula, by the way, works, again, for theta, assuming it's in radians, not degrees. You can try it. You can put the sine of, let's say, 30 degrees, which is pi over 6. If you plug in pi over 6 here, the sine of pi over 6 is a half. And if you try to do this with pi over 6, you will find that it gets closer and closer to it as you add more terms. Okay? Probably 3, 4, 5 terms will be sufficient. Today we're going to say theta is so small that you can throw all of these. All of this will be, if you cube theta, it will be just too tiny. And it will go away. And this formula here works, again, for theta in radians, and it works for any theta. Theta can be infinite, as large as you want. It converges, we say. You may have seen this in Calc 2 if you got that far this semester, or if you have already completed the course, you definitely saw this. The cosine of theta can also be written as 1 minus theta squared over 2 factorial. 2 factorial is 2 times 1, which is 2. And then theta to the 4th over 4 factorial, and then minus theta to the 6th over 6 factorial, and then plus theta to the 8th, and so on. So plus that. So it just goes on. For the cosine, usually we put the 1, or maybe we carry to the second term if it's small. If the angle is sufficiently small, it's just pretty much 1. If it's a little larger, then we may include this term. But today we're going to only include, we will just say the sine of the angle theta is so small, less than 10 degrees, then, whatever 10 degrees is in terms of radians, then sine of theta is almost theta, and the cosine of theta is basically 1, all right? It's basically 1. And you can try it on your own and verify this, provided the theta, you may think of it in degrees, but when you plug in theta, plug in radians, and it will be, the sine of theta in radians will be approximately equal to theta itself. Okay, so that's what I'm going to refer to. And so let's look at this pendulum, how it works. So you have a mass. I might do it in 2 different ways. Let's see. You have a mass and it's attached to a string. The string is of length L, and this is mass M, and you stray it to the right, you pull it to the right by an angle, by an amount of angle theta, and you let go. So the spring will oscillate back and forth. Okay, will oscillate back and forth. So I'm going to set my coordinates. Here is the x coordinate, here is the y coordinate, and we're going to make, let's work in Cartesian coordinates, and we will use approximations like that. And so what are the forces, first of all, in this mass? The forces are, this may be the easiest way to deal with it. You got the tension this way, and you got mg. These are the only two forces. And we're going to make two assumptions. The motion, there is no motion vertically because most of it is going to be horizontal because theta is small. You're not going to see much vertical displacement, so we'll just say the vertical displacement will be basically, there is no displacement vertically, and therefore the net force in the y direction will be 0, and there is only force in the x direction. So here is what we're going to say. So the tension will have two components, T. If this is theta, then this is theta, and this is the adjacent to it, so this is T cosine theta. And this way, you get the T sine theta. This is theta, and this is also theta. And we're going to look in the y direction. We're going to say the net force would be 0. The net force in the y direction will equal to the mass times the acceleration in the y direction. The net force in the y direction consists of the tension, cosine theta, that's upward, minus mg, that's downward, and equals to the mass times acceleration in the y direction, and we're going to say that it's simply 0. That's simply 0. And therefore, the tension times the cosine of theta will equal to mg, and since the angle is small, if theta is small, then the cosine of theta is basically equal to 1. And if the cosine of theta is 1, it means the tension is basically equal to mg. Tension is fairly close to mg. Alright? Tension is fairly close to mg. Not exactly equal, but fairly close. Now in the x direction, the net force in the x direction, it will equal to the mass times the acceleration in the x direction. ma. That's the acceleration in the x direction. Now the force, when x is positive, force is negative. And when x is, and when you're here, as you can imagine, when the pendulum is here, the t sine theta would point this way. So when x is on the left, the tension points right. And when you're on the right, the tension points, the t sine theta points left. And that's a restoring force. It always wants to take you back to the equilibrium. And so we know there will be oscillations. And so we have I'm sorry, what was it? On this side, you have the t sine theta, but it will be negative because it's opposite direction to x, always. But the tension is equal to mg, so we have negative mg sine theta will equal to the mass times the acceleration. Sorry. And now I'm going to use that small angle approximation again. The sine of theta will almost equal to theta, will be basically equal to theta. So I have negative g times theta. Instead of sine theta, I will write theta. And on the right hand side, I have the acceleration, and the acceleration is the second derivative of position. So the second derivative of x with respect to t. But I have theta here, and I don't want theta. Well, remember, if you have an arc that's like this, again, the whole displacement is in the x direction here. This is basically equal to x and this is theta, and the length is L. So L theta will equal to X. Right? The arc length will equal to L times theta. So theta will be X divided by L. So instead of theta, I'm going to write X over L. So I have negative G, and then X divided by L, I'll write it here, equals to the second derivative of the position with respect to time. And now see, you have the second derivative of a function gives you back the same function with a minus sign times some factor. And this thing here will be the frequency of oscillations. This will be omega. And so you get X as a function of time will be the amplitude, how far to the right you pulled it initially, times the cosine of omega t plus phi. And omega is equal to the square root of g over L. The period would be 2 pi over omega, and that is 2 pi the square root of L over g, because you're dividing, you reciprocate. Okay, so that's basically the conclusion here. We get this. Okay. Another way to do it is by thinking of it as a torque. Let me see how much time I have. Yeah, let me do it quick. So for an object like this, let's say you have a point mass here, and it's rotating about this fixed axis here, and it's oscillating back and forth. And so there is the tension, and there is the mg. Now, who contributes to the torque? The tension doesn't. The tension does not contribute to the torque. Only mg contributes to the torque, right? Only mg contributes to the torque. If this is theta, and this is theta, and this part of mg is what contributes to the torque. That's the mg, the force, so the torque. This part of the mg that contributes to the torque is the mg sine of theta. And it's a clockwise torque, so it will be negative. So this way it will try to turn it clockwise. When you're here, it tries to turn it counterclockwise. Again, it will be negative. There is that negative thing. So we know that the net torque on an object will equal to the mass times not the mass times acceleration, it would be the moment of inertia times alpha, which is the angular acceleration. Notice the tension doesn't contribute to the torque because the position vector is this way, the tension is this way, so there is 180, and torque is the force times distance times the sine of theta. Sine of 180 would be 0, and so tension does not contribute to the torque. Now the torque itself will be the force times the sine of theta, that's mg sine theta, would be the mg sine theta, that's the force part, times the sine, and then times the distance for the arm length, that's L, and it's a negative torque, it will be negative. When theta is positive, it will be negative. And then I alpha, what is I? Let me maybe keep writing this way. What is I? Well, it's a point mass, a distance L away from the axis of rotation, so it's ml squared. The mass times L squared. That's the moment of inertia for a point mass spinning about an axis that's L, distance L away. And then alpha is the angular acceleration. And so let me just write it as alpha for a moment. Again, the mass simply cancels. And again, we're going to refer to that small angle approximation. The L here will go away. So I have negative G. Theta, sine theta would be approximately equal to theta. And I have here L times alpha. L times alpha. Let's write it as L times, what is alpha in terms of the tangential acceleration? Alpha times r, if you remember, alpha r is the tangential acceleration, so A divided by r will give me the tangential, give me the angular acceleration. So alpha will be the linear acceleration, or tangential, divided by the distance, which is r, or L in this case. So L will cancel here. So I have just A on the right-hand side. Here I have G times theta, but theta is equal to x divided by L. And so I get negative g x over L equals to the acceleration. So I have the acceleration to be negative g over L times x, which is exactly what we had here, and the solution will be the same. All right? I'll stop here and then we'll go to the next video. So I just showed you two different ways how to do it. The second way would be helpful when we do the physical pendulum.